All right. There are some notes that I have that are printed. Hello, hello. Okay. So, like I said, we are talking about quantitative analysis today. I have a couple of examples for us to kind of think about. The first one is Amy Winehouse. Do you guys know who she is, musician-wise? I was going to offer to play a song of hers. Would you guys like to listen to a song of hers just for fun? Okay. So, yeah, I'll play the song first. You guys can enjoy that. Amy Winehouse did die. I don't know if you guys are aware of that. She died in 2011, so over 10 years ago now. And she died actually of alcohol poisoning. So I find that song quite ironic. She didn't want to go to rehab, and now she's not here. In fact, my uni professor at the time, so I do actually remember when she died because I was in my last year of my bachelor's degree. I started my toxicology course, or not started my toxicology, I was taking a toxicology class, and he made a joke about how she should have probably gone to rehab. Wasn't in good taste. It probably still isn't in good taste, but just something interesting to think about when we are talking about quantitative analysis, because obviously alcohol is something that we can legally acquire, but it can result in quite deadly consequences if you take too much of it, and this is an example of when you take too much, and it can actually cause alcohol poisoning. What else do I want to say? I was doing some reading just to kind of see what in particular happened, and they think that it was combined with her alcohol, so the overdose on the alcohol on top of the fact that she suffered from bulimia. So she wasn't in a good, healthy state in her body already. So the combination of those two things resulted in her overdosing. A lot of these times, you can throw up and you can aspirate on your own vomit. So you basically choke on your vomit and things like that. So it can be quite dangerous when you do overdose on alcohol. And I can go down a little rabbit hole with you guys if you want to think about toxicity and things like that. But let's get the lesson done first. Another example of when we want to have quantitative analysis is if you have diabetes and you're managing an insulin pump. So when you have diabetes, it can be type 1 or type 2. I gotta remember which way around it goes. Type 1, I believe, is the one that's juvenile, that you don't produce insulin. And so then your body is required to then have insulin to help manage your blood sugar levels. So when you eat something, you just had lunch, your body releases insulin from the pancreas, and that tells your cells to absorb the insulin that's floating around in your bloodstream, is what that is doing. Because you don't want it in your bloodstream, because if it's not at the right level, you can have hypoglycemia, which is when it's too low, your blood sugar is too low and you start fainting, or hyperglycemia, when you have too much sugar and it causes other problems, but I can't remember it off the top of my head. So that's type 1, typically known as childhood diabetes. So it's usually diagnosed sometime in childhood, and at that point you'll have an insulin pump that you wear, and that insulin pump will actually measure your insulin level throughout the day, and if you need more insulin, then it'll inject some more insulin into your body, so that way your body's actually absorbing the sugar like it's supposed to. So just some fun facts. Insulin comes from your pancreas, so basically your pancreas isn't making the insulin that you need. This is actually quite deadly if you didn't have insulin to replace it. So it's really good that we have this technology. But what that's trying to do is just measuring the concentration of insulin in your blood, measuring the concentration of sugar in your blood to make sure that we release the insulin in the right time frame, so that way your body actually has what it needs. Type 2 diabetes is the one that you tend to get with diet. So if you have a poor diet, your body can become resistant to insulin. So basically your body is producing the insulin, but your cells don't respond to it anymore. And so you know how there's insulin's a protein that floats around your body. There's a receptor on your cells that it bonds to, and then it tells it, okay, absorb the sugar from the bloodstream. What happens with that type of diabetes is that even though you have insulin in your body, it binds to the receptor, but it's not actually doing the next step, which is absorbing the sugar. That one they tend to treat with different medications. My grandma, my apo, she had type 2 diabetes, and so she was on certain medications to help manage that, and she'd also be removing sugar from her diet, so that way it was more manageable as well. So 2 examples of day-to-day life that you would actually need to kind of worry about concentration, but there's obviously lots of examples that work like that. The next kind of thing to talk about then is how do we measure concentration? So I do have some notes for you guys that I printed out because I thought it was good to see it. I'll talk about the proper way to do it, and then I'll talk about the way that it's actually getting done, or sorry, the way that you guys are going to do it. You can see some of my master's work actually. All right, so there are a few ways that we can measure concentration of an unknown substance. I'll talk about the first way because that one is what my master's was in, and then I'll show you guys what you guys are going to be doing. All right. Get my device. There we go. Okay. So let's talk about the fancy way, the actual scientific way, because I think it's good to know in context what we actually do as scientists, and then you guys will hear about how you're going to do it in the lab. But it's definitely something that you're going to be doing at some point because we do need to know about amounts. So just so you guys are aware, there are lots of different ways we can measure concentration. The main thing that we need to do is make a standard curve. So this is what that's showing here. Now, the way the standard curve works is I basically have standards, is what we call. Everyone has standards. So you have standards. And they're basically just samples that you make up of known concentrations. So they're known concentrations of whatever you're testing. There's lots of different ways you can do this. It just depends on what equipment and what you're looking for. For me, I was specifically looking at glutathione, which is abbreviated. Is this glutathione or is this something else? Let me just see. No, this is. All right, GSH. So that is, GSH is known as glutathione. Oh, now I gotta remember how to spell it. I don't think that's how you spell it, but that is the idea. Grab one of these sheets. Or not big sheets. Those sheets. We're talking. All right. I don't think I spelled glutathione right. Anyway, glutathione is something that is found in our cells and in our bodies. It is an antioxidant. You guys might have heard of antioxidants before, potentially? In like day-to-day, in a sense of like, oh, if you take this, this is going to be an antioxidant, and it reduces inflammation, is what you usually hear it about. So these guys basically mop up things that can cause damage. So you take a lot of antioxidants in various ways. So that's why I was looking at that in my cells, because it was a good way to measure if something was causing problems. So if I had low amounts of glutathione, what that told me is that it was being used in some sort of reaction, and so that tells me there was damage potentially happening. So what I did was I made standards with known concentrations. So these are some examples of what I have. So if you guys notice on the bottom, it says amount of glutathione on my column. So it's just basically saying how much quantity-wise, and I have it with increasing quantities of glutathione. On this one here, this one was the cysteine to glutathione ratio. Basically, I was looking at a fluorescent dye, and I was checking this ratio here, and then I graphed it like that. So you guys have probably seen these before. You would have done it last year if you guys remember the toy car experiment. And you did a linear experiment. You got y equals mx plus c. Just hopefully ringing a bell. Yeah? So I did the exact same thing when I was a master's student. I figured out basically my standard curve. I had known concentrations of my sample that I was testing. I had an absorption rate, so I was checking to see how much fluorescence I saw, and then I graphed it like this. And then from that graph, I got an equation. So I got y equals mx plus c, and then from there, you can then figure out unknown concentrations. And I did it on this machine over here, known as your HPLC machine. So high pressured liquid chromatography is what that stands for, if you guys are curious. So I used that expensive machine. It was probably about $500,000. And I basically made a standard curve, and then I would have unknown samples. And then if I had an unknown, what I basically did, let's say my unknown was here. So if I don't know the concentration of something, but I did know the absorptive absorption value, I could then correlate back to figure out concentration. Basically using and rearranging this y equals equation. So that's how we can figure out concentration of substances. Lots of different ways you can do that equipment-wise to get what you want. But that's the whole idea. If I have an idea of what my known is, I can figure out an unknown. Now, what you guys are going to be doing is slightly different. You guys are actually going to be using acid-base chemistry to figure this out. And you're going to be looking at equations, and you're going to be looking at neutralization. But the same concept applies. You have something that's a known concentration, and you're comparing it against something that you do not know. So for example, if I have an equation like sulfuric acid plus sodium hydroxide, and then it neutralizes, so that's my equation for neutralization if I was looking at it, and I think I haven't balanced it. No, I haven't. There you go. Okay, so in this chemical equation, I can see that for every one sulfuric acid molecule I have, I shouldn't say molecule, particle, compound, that's the word, I would need 2 sodium hydroxides. Are we okay with that so far? So this is telling me that I have a 1:2 ratio. All right. Now, if I manage to get this at the neutralization point, basically what I would have is my acid and my base would have neutralized each other, and I would have it in a balance like that. So what that means is once I hit that neutralization point, I can actually use this ratio. So if I knew my sulfuric acid concentration, then I know that the sulfuric acid, my base concentration needs to be twice as much as my acid concentration based off of this equation here. So we're looking at ratios. All right. So what you guys are going to be doing is a technique known as titration. You're going to have an acid in one situation, and you will have a base in another situation, which I am guessing must be in this guy. It's not labeled. So we have an acid and we have a base. The other thing that's going to be really important is an indicator, because that indicator tells us pH. It gives us an idea then if I am at that point where my ratios will work. You'll be taking a volume of an acid, pipetting it into a flask, adding indicator, and then you're going to be titrating it against a base. So I add that base, and we can measure off the burette, which is another piece of equipment, and we can figure out the volume of base we needed to hit that neutralization point. I can then use those ratios to figure out the concentration of the unknown. So if I know my acid concentration, I can figure out my base concentration and vice versa. You just need to know one of the two. Are you okay? Don't stress too much about it. We'll start doing this next week and we'll start tinkering. What else did I want to say about this? I'm trying to remember. Oh, this here, when you're using your equations to figure out unknowns, like quantity-wise, we call this stoichiometry. So we'll cover that again once we get to the calculation bit of this topic, but that's just something to keep in mind, is that we can use equations like this and the ratios of substance in those equations. And so long as the equation has equal amounts in order for the reaction to go to completion with no excess left over, then we can figure out concentration of something that's unknown. This is quite an archaic way of doing it. Like I said, in modern times, we tend to use this method instead because it's far more accurate. It doesn't depend on you getting exactly the neutral point. Questions, concerns, comments? We good? All right, just watching our time. What time did we finish? 40? Okay. So I'll give you guys two choices. Choice number one, if you guys want to play with some equipment, what I will do is I will get out some acid and base, and I will also get you universal indicator. And the aim of the game is to try to balance the acid and the base so that way they neutralize and they hit that neutral point and you get a green color. It's actually a lot harder than you'd think it would be. So that's option number one. Option number two, is anyone interested in hearing me go on a rant about toxicology? Or not really? You can do that while you're doing that? You want to do both? Okay, yeah. All right. It is interesting. All right, I'll stop it.